we need to understand chemical reactions. A chemical reaction is a reaction in which one or more substances are converted into one or more different ones. So a chemical reaction is a chemical change. In a chemical reaction, we have rearrangement and exchange of atoms like the Lego blocks. We're taking them apart and putting them back together in new ways, but the individual atoms, the building blocks, remain the same. A combustion reaction is a particular type of chemical reaction characterized by a substance combining with oxygen. And when it combines with oxygen, it produces one or more oxygen-containing compounds, and it releases heat. And the heat produced by the combustion is what is so important in supplying our society's energy needs. To describe a chemical reaction, we use a shorthand notation called a chemical equation. And, here's the bare bones of a chemical equation. The reactants are things that you start with, the things that are reacting with each other. And then there's an arrow telling you it's going in this direction, and the products are what get produced by the reaction. Okay? From a chemical reaction, we can get the formulas and states, like solid, liquid, gas, of reactants and products. We can get the relative numbers of reactant and product molecules, and then we can also determine, well, if I had this much, this mass of reactant, what mass of product could I expect? And so that makes chemical equations very useful. These are the abbreviations that we use in chemical equations to identify the state of a substance. G for gas, this is a lowercase l for liquid, S for solid, and we've seen this one, AQ, for aqueous, meaning dissolved in water. So methane is the simplest compound that undergoes combustion, and when methane burns, it produces carbon dioxide and water. So the methane is combining with oxygen. That's a characteristic of combustion. Combustion is something reacting with oxygen. So if we look at this, here we've got methane gas reacting with oxygen gas, and we're producing carbon dioxide gas and water in the gas state. But over here, this formula represents 2 oxygen atoms, and over here, carbon dioxide has 2 oxygen atoms, but the water molecule also has an oxygen atom. So we're starting with 2 atoms and ending up with 3 atoms. And that doesn't follow the law of conservation of mass. There's also a problem with the hydrogens. On the left side, the starting side, we have 4 hydrogen atoms, and on the right side, we only have 2 hydrogen atoms. So we could get creative and say, well, maybe the 2 hydrogen atoms that disappeared changed into 1 oxygen atom, and that would solve the whole problem. But in a chemical reaction, elements can't change into other elements. They stay the same. So we need to adjust our equation so that it describes reality. And this is called balancing the equation. So here we have the chemical equation in letters, and then we have space-filling models of these molecules, which can help us see what's happening here. So we need to put a 2 in front of the oxygen, so that when 1 methane reacts with 2 of these oxygens, it can form 1 carbon dioxide, so that black one is the carbon. It was with hydrogen over here, but now it's with 2 oxygens. So we used up 2 of these guys, and the other 2 are over here, and they're each with 2 hydrogens. So we need a 2 in front of the water molecule. And in this way, we can take the number of starting pieces and rearrange them and make the products, and we don't have any left over, and we don't need to borrow any atoms from anybody. So we're going to adjust how many atoms or molecules of each compound there are by putting a number in front of it. That's called the coefficient. We're not going to change the chemical formulas because that changes what the substances are, and that doesn't work. Any questions? Understanding chemical equations is very important. So let's practice counting atoms in a chemical equation. So this is saying how many oxygen atoms are on the right-hand side of this chemical equation. So the right-hand side means to the right of this arrow. So this 2 is telling me that there are 2 formula units of this. How many oxygen atoms are in one formula unit? 3. And I have 2 of them. So that's 2 times 3. So there's a total of 6 from this guy. And then over here, each molecule has how many oxygens? 2. And there's 8 molecules. So I have 4 times 2 is 8. And 6 plus 8 is 14. How many oxygen molecules are on the other side? 14. Here, there are 4 of this guy, and each has 3. So 4 times 3 is 12. We got 12 there. And this is just one O2 molecule, so that's 2, and that also equals 14. Any questions? How many iron atoms are on this side? 4. And how many over here? 4. Because each of these units has 2, and there are 2 units, right? So this is a guide to balancing equations. This is not a set of hard and fast rules. It's not a follow these steps and everything will be wonderful. It's just a suggestion. First, start out with a skeletal equation, meaning just get the formulas for the reactants and the products in there on the right side of the arrows. Then we're going to balance, and we're going to look at atoms that occur in more complicated formulas first, and we're always going to leave anything that's a pure element to the end. So we go with the more complicated things first, and then the stuff that is just an element. And then if in the process of doing all that we end up with coefficients that are fractions, we're going to clear those by multiplying all the coefficients by the denominator of the fraction. But I'm going to show you how you can generally avoid using fractions as your coefficients. And then always go through and check it at the end. So the way these problems are set up, we're going to get some practice in nomenclature, okay? So write a balanced equation for the reaction between solid silicon dioxide and solid carbon to produce solid silicon carbide and carbon monoxide gas. So as we look at this, that's okay. So we have the reaction between this and that, so this and is a plus, to produce, that's where the arrow goes, this and that. So we need to take the names and translate them into formulas. So silicon dioxide, is that molecular, an acid, or ionic? Is molecular, because if we look at silicon, it's to the right of that line. It's a nonmetal for naming purposes for sure. So for the molecular compounds, we're going to use prefixes. There's no prefix on silicon, so that must be just one silicon. And dioxide means 2 oxygens. What state is this? It's solid. Now, there's no way you would be expected to know that, but they tell you right here. Okay, and then we need a plus, and I'm going to leave some space because I might need a coefficient. What's the formula for carbon? Just C. Carbon is not one of the diatomic elements. This is where you do need to keep track of that. So it's just C, and it's a solid. And then there's this guy, silicon carbide. Well, silicon, again, is a nonmetal. Carbon's a nonmetal. This is a molecular compound. It maybe should be called silicon monocarbide, but we can do okay here. So it doesn't work anymore, but I used to be able to ask Siri, what's the formula for silicon carbide? And she'd say SiC. S-I-C. It was fun, but she didn't do it anymore. So that's a solid. And carbon monoxide gas, what's the formula for that? CO. And we need to make sure that that O is a capital O, and this is a gas. So this is my skeleton, the correct chemical formulas. Now we can balance. So, they gave suggestions about doing the thing in the most complicated compounds first. It actually works out pretty well most of the time if you do the first element first, and then do the second element, and just kind of go through that way. So this is called balancing by inspection, meaning we're just kind of looking at it. So what we want to do, so we've got this division here of before and after. We want to make sure that we have the same number of atoms before and after. So the first atom here is a silicon. How many are there? One. And how many are over here? Just one. So that's good. We don't have to mess with it. How many oxygens? Two. There aren't any more over here, so they've got a total of two. And over here, how many? One. How can I make that into a two? I'm going to put a 2 coefficient. I'm going to need 2 of those molecules. I can't change the formula to CO2 because that's not carbon monoxide. And now I've changed what the reaction is. That's not okay. And then here I have 1 carbon, and how many carbons on the right side? There's 3. This one's kind of hiding here. So here's carbon, and then there's 2 more carbons, and so that's a total of 3. Any questions? If you can visualize these being little, balls of different colors, the silicon might be green or something, and the oxygen's red, and the carbons are black. And you need to come up with the right number of them on each side so that you can take these things apart and make the products and use up all the little balls. That's what we're doing. Write a balanced equation for the combustion of gaseous ethane, a minority component of natural gas, in which it combines with gaseous oxygen to form gaseous carbon dioxide and gaseous water. So much gas. So combines with to form that and this. So the words in the sentence help us out here. So they gave us the formula for ethane. So C2H6. And they said it's a gas. Plus, and I'm going to leave a space, gaseous oxygen. What's the formula for oxygen? O2. Because horses need oats for clear brown eyes. And this is a gas. And then the products, carbon dioxide, what would that be? CO2. It says that's a gas. And water. It's a formula for water. H2O. Water is a gas here because when ethane burns, it's hot. It's fire, right? Fire is hot, and so the water that gets produced in this hot environment is a gas, not a liquid. Okay, so I'm going to show you a different method of balancing an equation. It's sort of like taking inventory, because sometimes they get a little more complicated. We've got oxygens over here, and these combustion ones can sometimes get a little messy. So this is one way to balance. If you like it, use it. If you don't, don't. So I'm just going to look and see what elements I have: carbon, hydrogen, and oxygen. And so there's carbon, hydrogen, and oxygen. And I'm just going to go through and find out what I've got. So in this, there are 2 carbons and 6 hydrogens and no oxygens. And over here in O2, no carbon, no hydrogen, and 2 oxygens. How many carbons in CO2? How many hydrogens? None. How many oxygens? 2, CO2. And H2O, no carbons, 2 hydrogens, 1 oxygen. So I'm looking at the total for each side. So here for oxygen, I have 2 plus 1, which is 3. And this one's 2, and that one's 1. And over here, that's 2 and 6 and 2. So nothing's balanced. Oxygen is at the end, which is appropriate because here we have O2 by itself. The reason we want that at the end is because if we put a coefficient in front of O2, it's not going to mess up carbon or hydrogen. Whereas if we had to use hydrogen last and put something here to balance the hydrogen, that would change the oxygen, and we'd have to go back and fix that. And you end up going in circles, and nobody likes that. So I have a total of 2 carbons on the left side. I have 1 on the right side. How can I make there be 2? I can put a 2 in front of CO2. So that changes this to 2 carbons, but it also changes the oxygens, so I have 4. So now this is 2, and this is 5. Here I've got 6 hydrogens, that's my total, and over here I have 2 hydrogens. How do I make a 2 into a 6? Multiply by 3. So multiply this by 3. So 2 times 3 is 6, and 1 times 3 is 3. So I'm just, changing these as I change them. And when I did that, I didn't mess up any of the carbons. So I've got carbon and hydrogen balanced. And now I need to balance the oxygen. I have 7 oxygens on the right side, and I have 2 on the left side. So making 2 into 7 is a little trickier than making 2 into 6. Because these oxygens come in pairs, you can't order up 7 oxygen atoms. You're either going to get 6 as 3 molecules, or you're going to get 8 as 4 molecules. They won't let you buy half of one. So this is what I call the odd-even problem. I need an odd number of this element, but it's coming in pairs, so whatever I do over here is going to be even. Right? So this is where we could use fractions. We could put 7 halves. That's not very good, 7. 7 halves. 7 halves times 2 is 7. And then we'd have to clear the fraction by multiplying everything by 2. Most students don't like that. So to solve the odd-even problem, if we multiply everything by 2, then the odd number becomes even, right? So I'm going to multiply everything by 2. So it's going to be 2, changes to 4 and 12. And I'm going to leave this one alone because this is the one that we're messing with. This is the question mark right here. And I'm going to change this 2 to a 4, which makes this 4 and this 8. And I'm going to change my 3 to a 6. And so this becomes 12 and 6. Now over here, this is 4, 12, 8, and 6 is 14. Over here, this one now, the total is 4 and 12. So doing that, I didn't mess up carbon and hydrogen. I just doubled everything, and so the carbon and hydrogen are still balanced. Now I have 14 oxygens on the right side, and I look over here, and they're coming in pairs, right? So I need 7 of them. So now I can use a whole number, an integer, put a 7 in there, and this becomes 14. And everything's balanced. You do not have to do it that way, but sometimes when things get a little messy, that can help. If you start doing a balancing equation problem and you find that you're going in circles, like, I balanced the carbon and the hydrogen, now I'm doing the oxygen, but I'm changing the carbon. So I fix that, and then it's like I'm just changing things all the time. Start over. Double check that your formulas are correct. If your chemical formula is wrong, it may be impossible to balance the equation. If your formulas are all correct, then just start with a different element. Because most of the time you can start with the first one, but not always. Write a balanced equation for the reaction between aqueous lead 2 nitrate and aqueous potassium chloride to form solid lead 2 chloride and aqueous potassium nitrate. So here we've got and to form and. Now this one, ionic compounds with polyatomic ions. So here we have lead 2 nitrate. So we learned that to write the chemical formula, we need to write the formula for the 2 different ions with their charges so we can see how we need to put them together. So I'm going to do that up here. Lead is Pb, and what does the Roman numeral 2 tell me? It tells me the charge. That's not the subscript, it's the charge. This is a 2+. And nitrate is NO3 minus, because you memorize it. So if I want to put these together and have a neutral compound, how many nitrates do I need? 2. And this is a polyatomic ion, so I need to put the shrink wrap parentheses around it and put the 2 on the outside. And then we're told that it's aqueous. Might need a little more room. Okay, plus potassium chloride. What's the symbol for potassium ion? K with what charge? +1, because it's in group 1A. Everybody in group 1A +1. And chloride comes from chlorine, and the charge is -1. Because on the periodic table, we start at the noble gases. Argon is 0, and you go backwards, one square, -1 to chlorine. So we can look at these guys, and +1 and -1, we just need one of each. So we'll push those 2 guys together, and we're told that it's aqueous. Now, it's actually kind of convenient that we have these written out because the products here contain the same ions, they're just put together differently. So here we have lead 2 chloride. So that's this guy, lead 2, and chloride. So what's the formula for that? PbCl2. And we're told it's a solid. And then we have potassium nitrate. So here's our potassium ion and our nitrate ion. Whoops. Didn't wait for the lasso. So what's the formula for this one? It's KNO3. Well, that kind of looks like an X. That's not good. K. And that one's aqueous. So what I'd like you to recognize is that this nitrate ion was present as one of the reactants, and it's also present as one of the products. It didn't come apart. It's still together. So it's like a little subunit of your Legos that, 3 of this and 1 of the other, and that part stays together. You just take the whole module off and you stick it on something else. You didn't have to take it all the way apart to atoms. So when we balance this equation, we can treat the nitrate as a single thing. If you don't like that, you can do the nitrogens and the oxygens separately. There's nothing wrong with that. So now let's just start at the beginning. The first element is lead. And so on the left side, how many leads are there? 1. And on the right side? There's just 1, right? Okay, so that's nice. How many nitrates? 2. And over here, there's only 1. So if we need more of the whole compound. So it'll be 2 of the KNO3s. That'll give us 2 nitrates. Here we have 1 potassium. And over here now we have how many potassiums? 2. So I need to put a coefficient of 2 in front of KCl. And now, fingers crossed, how many chlorines? 2 and 2. And that one kind of took care of itself. Any questions?